Okay, this is section 3.5, and we're going to be finding limits at infinity. And we've kind of already done this at the very beginning of the year when we were discussing limits, but we never really found limits as x approaches positive infinity or negative infinity. And you may be wondering why they throw this limit lesson in the middle of this chapter. It's because as we're finding limits as x approaches positive infinity, those limits are going to show us where we have horizontal asymptotes. So when we start graphing our functions given the derivative or the second derivative, it's going to help us to know where we have vertical or horizontal asymptotes. And so limits at infinity will help us find those horizontal asymptotes. So just a quick review, and I know this isn't on your notes, but I have graphed this equation, f of x equals 3x squared over the quantity x squared plus 1. Okay, so when I graphed that, here's the graph of that. And we know that we can find limits lots of different ways, 3 different ways. By a graph, by a table, and then algebraically. And remember, when we find a limit, we have to find the limit as x approaches that number from both sides. But in this particular problem, I'm finding the limit as x approaches positive infinity. Okay, and then we'll look at negative infinity. So if I just look at this graph, as x approaches positive infinity, or as my x numbers get larger and larger and larger, do you see that this graph seems to flatten out? And it seems to flatten out at 3. Okay, and same thing when as x approaches negative infinity. All right, as x approaches negative infinity, it flattens out again. And where that graph flattens out, that is a horizontal asymptote. So the limit as x approaches infinity is 3, and the limit as x approaches negative infinity was 3. Now we can also find the limit using a table. As x approaches positive infinity, I entered in, that's an infinity symbol by the way, numbers that got bigger and bigger and bigger. And as those numbers got bigger and bigger and bigger, they got closer and closer to 3. And I know these say that it actually equaled 3. My calculator just rounded off because it got so close to 3, it just rounded. And then same thing here as x approaches negative infinity. I entered smaller and smaller numbers, and again, my calculator just rounded to 3. So the limit was x as x approaches negative infinity is 3. So today we're going to talk about how we would find those limits without the use of a calculator. So we're going to discuss how to find those limits algebraically. So the first thing I want you to look at on your notes, skip over those guidelines first, and I want you to look at Theorem 310, limits at infinity. And it says if r is a positive rational number and c is any real number, then the limit as x approaches infinity of c over x to the r is 0. And then they give you the same thing if x is approaching negative infinity. So what are they talking about here? C is any constant, so I'm going to say that constant is 5. I don't know why it does that. Hang on. Oh, hang on. Okay, let me erase all this. My computer just went crazy on me. All right, so let's say our C right here is 5, so I'm finding the limit as x approaches infinity at 5 over x to some power. We don't know what that is. Let's just say it's 5x squared. Well, doesn't it make sense that if I put 5 over some huge number, infinity squared, let's just say it's 1,000,000 or 10,000,000 or 10 billion, okay, that as x gets bigger and bigger and bigger on the bottom, that number is going to get smaller and smaller and smaller, and eventually it's approaching 0. That just kind of makes sense. As this number gets bigger and bigger, okay, this number 5 over, 10 billion is a really, really small number, and the bigger my x number becomes, then I approach 0. And same thing for negative infinity. Okay, so this is the theorem that tells us a constant over x to some power will always equal 0 when I'm approaching positive or negative infinity. So let's see what that looks like. Example 1, I'm supposed to find the limit as x approaches infinity of 5 minus 2 over x squared. Okay, well we know that the limit as x approaches just a constant is just that constant. So this part is 5 minus, okay, this is the theorem we just talked about. So the limit as x approaches infinity of this number is going to get bigger and bigger and bigger. So that's going to be 0. So my limit is 5. Okay, so now let's do another one. Now, when I have something like this, okay, I don't have everything broken down. It looks different than this. Okay, so here's how you're going to do this. You're always going to look at your denominator and take your highest exponent. So my highest exponent is x to the first. All right, so I'm going to divide each term on the top and the bottom by my highest exponent. And then I'm going to simplify and I'm going to show you what that looks like. So here's what I'm talking about. I'm going to take 2x. And since x to the first is my highest exponent, when I say highest exponent, I'm talking about the exponent over your x number. So 2x over x minus 2 over x over x plus 1 over x. So I just take each individual term and divide it by this x. Now I'm going to simplify. These x's will cancel and I get 2 minus 2 over x. X over x is 1 plus 1 over x. And now do you see what we have left? We can now use that theorem that we talked about. The limit as x approaches 2, the limit as x approaches infinity of 2 is just that constant 2. Do you see that this limit is 0? The limit of this is 1 plus 0. So the limit is 2. Okay? So let's do another one. All right, example 3. Okay, I'm going to do the same thing, but this time I'm dividing by x squared. And even though this x squared number has a coefficient in front, we're only dividing by the x squared part. So I'm going to take each individual term and I'm going to divide it by x squared. And so I have 3x squared over x squared plus 1 over x squared. Okay, so let's simplify. Here I would have 2 over x plus 5 over x squared over, here do you see my x squared cancel, and I have 3 plus 1 over x squared. So now I'm going to find the limit as x approaches infinity of each one of these. Well, this, do you see it's just going to be 0. This is going to be 0. The limit as x approaches infinity of 3 is 3 plus 0. So I have 0 over 3 or 0. Okay. Let's look at example 4. Okay, so example 4, this time our largest exponent in the denominator is x squared. So that's what I'm going to divide each term by. So I have 2x squared over x squared plus 5 over x squared, 3x squared over x squared plus 1 over x squared. Okay, and I'm going to simplify all this. So that's 2 plus 5 over x squared. That's 3 plus 1 over x squared. So do you see that the limit as x approaches infinity of this is just going to be 0? So I have 2 on top. This is going to be 0, so I have 3 on bottom. So 2/3 is the limit. Now, let's stop for a minute and let's go back and look at what you have on the top of your paper, the guidelines for finding limits as x approaches positive, negative infinity. So here's the thing. I showed you one way to do it. Okay, that's what we've been doing. Dividing by your largest exponent. Okay, so here's another way to do it. If you remember back in pre-calculus and in algebra 2, when you had to find horizontal asymptotes, you had a set of steps that you had to follow. Okay, and the steps were this. You had to first, and I don't know why I didn't write this up here, but first you had to compare the degree of your numerator and denominator. And when I say the degree of the numerator and denominator, your degree is your highest exponent for each. And then once you find the degree of your numerator and denominator, you're going to look and see which one of these does it follow. So the first one says if the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. Step 2 says if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. I'm going to show you what that looks like. And number 3 says if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. All right, so here's what that looks like. Let's start with this one. Let's find the degree of my top and the bottom. Well, the degree of the top is 1. The degree of the bottom is 1. I'm looking at the highest exponent for each. So my degrees are 1 and 1. So look at your notes. This would follow rule number 2. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. What does that mean? That means my leading coefficients is 2 over 1, because there's a 1 here, and that's my answer. So do you see that I got 2 here and 2 here? And this was a much shorter way. There's no math involved here. So again, I found the degree of my numerator, degree of my denominator. They were the same. So the limit is the ratio of the leading coefficients, 2 over 1. Okay, so let's do another one. Okay, the degree of my numerator on example 3 is 1. The degree of my denominator is 2. So on my steps, this is rule number 1. The degree of the numerator is less than the degree of the denominator. So I automatically know that the limit is equal to 0, which is what we got. Okay, so if you can tell just by looking at the degrees, then you can just write down your answer. If you forget the rules for the degrees, then you have to do it this way. Okay, let's look at this one. The degrees are the same, so my answer is the ratio of the leading coefficients, 2 over 3. Okay, now when I say ratio of leading coefficients, I always write my numbers in order, in descending order. So like an x squared plus an x plus my number without anything. Okay, all right. So let's see if we can use our shortcut on this. Let's compare the degrees. The degree in the numerator is 3. Degree of the denominator is 2. So look on your rules. This should be rule number 3. Rule number 3 says, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. Okay, so D and E, which means this must go to positive or negative infinity. All right. Now, this one's a little different. Okay. Let's compare our degrees. The degree of my numerator is 1, and you have to be careful. The degree of my denominator, this is x squared, but it's the square root of x squared. So that's actually x to the first. So I know it's maybe hard to see, but my degrees are actually the same there. So if my degrees are the same, that's rule number 2, and it says take the ratio of the leading coefficients. So my answer here would be 3 over the square root of 2. Now, here's one thing you have to be careful with when dealing with something underneath the radical. We know that when we take the answer of a square root, I have a plus or minus in front. Okay, so in this problem, my answer is going to be plus or minus 3 over square root of 2. Well, doesn't it make sense if I'm going to positive infinity, my answer is going to be positive 3 over the square root of 2. But look at example 7. Example 7 is the same exact problem, okay? But I'm going to negative infinity this time. So my degrees are the same, so I need to take the ratio of the leading coefficients. But this time it's going to be negative 3 over the square root of 2 because I'm going to negative infinity. All right, so the ones that involve a square root sign, you need to kind of look And C, are you going to positive or negative infinity? And that will determine your sign of your answer. All right, we're almost done. Example 8. Find the limit as x approaches sine x. So remember what sine x looks like. Sine x goes like this. It keeps on going. So as x approaches infinity, what do my y values approach? What do you see? They go up and down, up and down, up and down. Okay, so this is an oscillating function, so my limit does not exist. Now, example 9, this is a special trig limit. The limit as x approaches infinity of sine x over x. Okay, I meant to have the graph of this, but I don't. If I were to graph this, okay, this is a special trig feature or function. The limit of x approaches infinity of sine x over x will always be 0. And they use what they call the sandwich theorem on this. But that's one of those that you probably are just going to have to memorize. Okay, the last thing I want you to do is I want you to write down the definition of a horizontal asymptote using limits in that definition. So remember, all these limits that we've been finding as x approaches infinity or x approaches negative infinity, then that was where my horizontal asymptote was. So write down the definition of a horizontal asymptote. If you're not for sure, it is in your book under section, what is this, 5, 5, 3, 5.